Okay, let's go for this. Um, I think my last lecture was ended, or at least had this, and that's a pretty complete, I would say, philosophical or metaphysical or religious or whatever you want to call it, view of the world in which we live in. Where I said, like, everything is real, right? We live in one world. You, me, we can agree on, and I'm going to go there where I didn't want to go, is on Wittgenstein, Tractatus Logico-Philosophicus. His first proposition, die Welt ist die Gesamtheit der Tatsachen, nicht der Dinge. I think he goes wrong from the start in the sense that he doesn't explain what Tatsachen are or what der Dinge are. Der Dinge is, I would say, it's stuff, it's opinions, it's beliefs, it's mathematical models, it's these weird quantum theories or whatever. It's stuff. And he opposed it to Tatsachen. Tatsachen are, it's a German word, facts, and facts are something that I would say we can agree upon. So the scientific consensus, I think, on things are that we can agree on things that are moving into space. They are moving in space. Sorry, not into space. So we have motion, special relativity theory, and time and distance are real, not so real. Space-time, whatever, they are connected to special relativity theory. And then based on that special relativity theory, we built a system of equations, Maxwell's equations, which have the problem that, we talk about things in continuous things, charge densities, currents. Currents are the amount of charge that passes through a certain surface area or a certain point by amount of t. And you wonder then when you go through, when you think about elementary ring currents, where you sort of say, we have a ring current plus or minus 1, and it passes through, at a certain rate, frequency. Every so many times in a second, the elementary current passes through. So then you have near, far fields, and you really wonder when do Maxwell's equations really hold for this kind of discrete analysis where we have an elementary ring current going through a point, goes round and round. We have this elementary charge going through this surface area or through this point. I don't think infinitesimally small surface areas exist. They're differentials. Where do math and physics meet? So yeah, but that's what we have. We have all these relative things, time, distance in the first place. They're not categories of the mind. They're real, mass, force, energy, momentum, etc. But they're connected to sort of these absolute quantities that we have discovered in a variety of equations that you can reduce or not reduce into a simpler or a more complex form. Maxwell's equation, Schrödinger's equation, the equation of motion for an elementary charge, the Breuil's equations as they apply to matter particles and light particles. I write it here as Planck's quantum of action as a vector, and the momentum, linear or orbital. Linear as it related to linear or angular momentum, I should say, to be precise. And then the Planck-Einstein relationship, energy is equal to this mysterious unit in nature that prescribes how things are actually quantized in nature, times a frequency or h bar times a reduced frequency, the number of radians per second rather than the number of oscillations per second. So that's reality, and now we sort of should bring it down to making sense of old and modern quantum physics. To go back to that, I think it's really what I'm going to present now is where old and new quantum mechanics meet. I want to show you, that's where I show, when you want to reduce an interval between 0 and infinity to something between 0 and 1, or between 0 and c, or between whatever 0 and finite quantity, is that you will have a Lorentz factor involved. The Lorentz factor is really just this. The linear versus the circular view of things. X squared plus y squared is 1, or the radius, but I'm talking about the unit circle here. So y will always be equal to 1 divided by the Lorentz factor. So I'm going to jump straight into the matter is sort of new quantum mechanics, or the Heisenberg or the Bohr-Heisenberg interpretation of quantum mechanics is that we can only think of physical theories in terms of probabilities, and we do not really care about where these probabilities come from. We are not really interested in the physical processes that determine these probabilities. It's a pretty nonsensical statement in the sense that if you look at it, you're always going to end up with some kind of base states and the combinations thereof, and in the end you will need to normalize things. You will need to say sort of why you select not the base states, but sort of the various variables that explain why one combination of base states turns into another combination of base states, and that's the depicant consistency. So you wanna represent base states, which I think of in the end, molecules are very complicated, atoms are very complicated. You want to represent them by some kind of combination of a wave function of elementary particles. And what are the elementary particles? They're stable particles, electrons and protons. And that's where I have the model that I explained in so many previous videos, is that you have the energy mass equivalent relationship, which basically says mass is sort of a measure that you don't need because it's the inertia to a state of change of motion of an oscillation of charge, and the ratio between the energy in that oscillation and that mass factor will be equal to c squared. That's the mass energy equivalence relationship, and we can write it as vector equation. Then we have the Planck-Einstein relationship, which you can write in various forms. Generalized expression is it's n times h bar times sigma, but this n, when you look at the Bohr orbitals and the fine structure of an atom and the hyperfine structure, n is not necessarily actually a natural number, 1, 2, 3, 4. But for an electron it is 1. And we have this idea that an electron would be, a two-dimensional oscillation of charge, cosine and a sine combining to make the charge go round and round. Is it a definite model? I don't know. I sort of pull up an old figure here that I put when I was still publishing on Pixar rather than on ResearchGate. It's sort of, we can imagine that a point like charge would be orbiting around some center, and the motion would be chaotic, but it would be orbiting around the center, and sort of the linear distance between that center of oscillation and where the charge is, that if you fold that into a orbital wavelength, an orbital picture of things, then it may be chaotic. But again, we don't know. So the only thing we have is that an electron is like a Schrödinger set, a zeta-beweging charge orbiting around and forming some kind of, what Professor Clay said, a particle in the sense that it has a definite size and it interacts with photons, which are linear. And there I'm going to go straight to my theory of interaction. Yeah. Here it is. We have a photon coming in. We have this charge going around and around and around. And so there's several possibilities. Either the that's what elastic scattering suggests. It hits the charge directly, and so that charge, its motion will absorb the energy of the photon, which is electromagnetic, and it will disturb the electromagnetic field that is around it, because the charge will no longer have that easy circular current. It will change. Kinetic energy will change, and the kinetic energy of the electron as a whole will have some direction. The electron may be moving in this direction, now it will be moving in that direction, because the circular ring current will have another orientation. Or else, we say it, the magnetic field inside of this ring current is enormous, homogeneous according to classical electromagnetic theory, but it's humongous. Outside, it's more diffuse. This is not a picture of the near field, but the far field. It's going to fall off very quickly. And so we assume that a photon, which is far away from the classical, sorry, not from the classical, but from the Thomson radius of that oscillating charge, is not going to be disturbed, and it's just going to travel straight through and not interfere with the electromagnetic field. Yes, no. What I want you to know, this is pretty much an idealized picture of what happens. Thomson and Compton scattering are really, theoretical approximations, I would say. In reality, scattering of photons by charged particles is explained by Rayleigh scattering, by Bragg's law, crystal, the Mie scattering theory, and you will find that the differential cross-section for scattering is, it will depend actually on the energy of the incoming photon. Unlike what I put here, where it only sort of the scattering depends on, if the photon hits or not the hard charge inside of the electron, or the electromagnetic field inside of the ring current, and outside it doesn't. Things are not so clear. Things are confused, and in reality, a cross section does depend on second, third, fourth order factors that are proportional to the first, second, third, fourth order of the frequency or the energy, because frequency and energy are related through the Planck-Einstein relationship, of the incoming photon. So it's not a neat, nice picture where we have either hard scattering or elastic scattering or no scattering at all. That's a simplistic view of the world. We wanted to be here where I said, like, okay, idealistically you have a Compton radius that comes out of the formulas, very simple, the mass energy equivalence relationship and the Planck-Einstein relationship, and then it's really very simple, a tangential velocity. If you imagine a naked charge, which probably is not infinitesimally small, will be equal to the radius of the oscillation times this frequency vector, which is an axial or a pseudo vector. And you arrive at that. For the proton, the only difference we had, as said in our previous model, is that you get more bang for the buck, because we think of a proton as a three-dimensional oscillation. The naked charge is a chord and generates an electromagnetic field that keeps it in place in 3 dimensions, and there you're gonna have more bang for the buck, more bang for the energy divided by the radians per second is going to be 4 times h, and that's just the surface of a circle versus sphere is the difference between OPR squared and PR squared. So we have that factor 4. So you arrive at this, which has been experimentally confirmed. a proton radius, and then now we wanna go to probabilities. If we have an electron, probabilities, and the probability of scattering is of course going to be related to the fact that this there is scattering radius and the contour, it's contour radius, and we can, and this is the big thing about it, about Schrödinger saying that my wave equation, Schrödinger's wave equation, is not about probabilities only. It's about really the equations of motions of the naked charge inside. That's the Zitterbewegung hypothesis. And so, yeah, we will have a wave functional representation of what an electron actually is. Its contour radius times, the velocity is very high, c. We don't know where the charge actually is. It's probably where I want to show my, yeah, here, the idea of uncertainty. The precision of our measurements may be limited, right? That's an Ungenauigkeit. That's clear. Our measurement may also disturb the position, and so that's an Unbestimmtheit. And then, where quantum mechanics went wrong is that this uncertainty should be inherent to nature. It's Ungewissheit. And that was elevated to dogma. Yes, it was. But so what you have is, when you talk about amplitudes, we have here a wave function. The amplitude of the oscillation times the wave function itself. We're going to square it, and we're going to take the square of the absolute value, and we get some kind of surface area, the Compton radius of the electron squared. And of course, then we can relate that to a lot of things, but that's sort of where I want you to know that probabilities are rooted in, physics. A probability has to be, this kind of surface area or an energy density or whatever in a system that has more than one state. Here we're talking about an electron, so it has only one state. We may speculate about excited states, and I can do that, but I won't do that here. Is that the normalization will consist of sort of relating that surface area to an electron will be in an atomic orbital or a molecular orbital, and that has a certain surface or area of interaction, and that's what it's about. The big question remains, of course, is this ring current model is what happens when you look really, really close at it. Can we really identify a current defined by elementary charge time the frequency which passes through a certain point, with sort of Maxwell's equations, which basically talk about charge in general, an amount of charge that passes through a point at per second. I don't know. The jury is out on there. Let's go to the proton. I said for the proton you get like more bang for the buck, in the sense that it's a three-dimensional oscillation. So the energy per radian of its frequency, which will be much higher, will be 4 times the contour radius, h times c divided by the energy of the particle. And that's sort of kind of problematic in the sense that you have a factor 4 there, which I said can be explained by just the simple 4 factor that you have in the surface area of a sphere as opposed to the surface area of a ring current. But you wonder, like, what are the equations of motions for a charge orbiting around a sphere rather than, a planar oscillation? I talked about that in my previous lecture or lectures, where I said like it's really not easy to sort of develop a wave functional representation of the proton. We of course have the general definition or mathematical representation of point that moves on a sphere. It will obey this. X will be the radius of that sphere times sinus the polar angle times cosine the azimuthal angle, and I will be r times sine of the polar angles times sine the azimuthal angle, and z will be r times the cosine of the polar angle. And so yeah, it's very easy to write this, that a radius vector is xyz, with xyz being what we write here. The thing, of course, is when you develop a proton model, you want to find you want to define the polar and the azimuthal angle as a function of t, and for that you need to sort of say like, okay, how is gonna what's the derivative of phi? I think it's phi, not psi. Yeah, phi in regard to t. So we will have a certain frequency in the xz plane, and we will have a certain frequency in the xy plane. But the thing is, these are not going to be these regular functions that you have in a two-dimensional particle. The frequency in the xz plane is not a linear function of time, and the frequency in the xy plane is not a linear function of time. So that's not easy. That's not easy to solve. We still want to be thinking of a wave function for the proton, right? To sort of that's something I'm going to do in later lectures, related to the mainstream framework of wave functions, wave equations, and explaining real life scattering experiments, and explaining what the size of a proton or an electron actually are. I'm gonna go forward here. A quantum radius, an RMS charge radius, a scattering cross-section. They are not the same thing. But at the same time, I want to give you some mathematics here. It's sort of, imagine, regardless of a proton or a photon, imagine that we have an electric and a magnetic field vector, which may or may not be constant. We will assume they're not constants. We will assume that you can write E as some kind of cosine of some phase function delta, oscillating between 0 and 1 times the magnitude of that vector. It can be an RMS, or it's sort of a maximum, right? That's a poor explanation, but you will understand sort of the intuition. We have a bivector of a electric and magnetic field vector, and I said if you apply all of your conventions, right, your conventions for the XYZ orientation in space of the XYZ axis, and then sort of what clockwise and counterclockwise means. Folding, what it means for me is that you fold the x-axis into the y-axis once you have determined a right-handed coordinate frame. We will have always the situation that the electric and magnetic field vector are are, are perpendicular, orthogonal to each other. But then you say like plus or minus. The formula is this: is according to classical electromagnetic theory, is that the magnetic field vector will be minus I times interpreted as a rotation vector times the electric field vector divided by C. Conversely, the electric field vector is plus C times the magnetic field vector, rotated over an angle of 90 degrees. This is where I have a few papers on quaternions and how useful Hamilton's imaginary units I, J, and K are. But it's sort of a thinking of an imaginary unit I as a rotation operator, as I do, is not quite compatible with the customary interpretation of the imaginary unit, like put them here in a spherical. I is just the direction of x plus x, j is just in the direction of the unit vector in the direction of the positive y-axis, and k is the unit vector in the direction of the positive z-axis. That's not how it goes in my model. If you think of wave functions and how you should use quantum mechanics, I is not equal to the unit vector along the positive axis, and j is not equivalent to the unit vector in the positive y direction, and k is not equivalent to the unit vector in the positive z direction. Think of these EMB vectors, bivectors. That's where we are still looking for sort of a special. It can rotate around in this direction or in some other direction in any plane, but we have a rotation of an EYB plane in some other angle, in some other rotational plane. And this is where, for the proton model, as said, we're thinking of a radius vector. We think of a certain frequency and tangential velocity c, but we cannot directly relate it to the polar azimuthal angles, the nice x, y, z coordinates of our. We need to think in terms of dynamics, and that's not so easy. The thing you have to do with the proton is that you, just like you can imagine some EYB plane having some kind of funny oscillation, not necessarily and probably not opposite to the EMB plane. No, you will have an angle or sort of this imaginary unit J, which will say a proton basically, it's a ring current, it goes around, but this plane of oscillation moves around, and it can moves around and can just go like be a sort of like an accordion, or we more think like it rotates around, and that's a different model, but it's a model we believe in. But the plane as a whole is going to be rotating, and that's the thing. It's sort of this plane. This ring current is going to be rotating, but it's also going to be an orbital rotation, not a linear displacement. You will say, what evidence do you have for that? Well, that's the thing. It comes out of my proton model, where I say like, I think of a naked charge in oscillating in 3 dimensions. So we could write the wave function, just like we wrote the wave function of an electron, and it's sort of, the radius times Euler's number times J a rotation operator. But the rotation operator needs to rotate within a certain plane, and we don't know the plane. The plane itself is oscillating. Times what we do know is that the polar angle of the plane of rotation of the ring current of a proton is going to be the polar angle. And that's sort of more or less consistent, because if you write it out, the phi is going to be the radius of the proton vector times Euler's number times set J. And if you write it out mathematically, you will have the cosine of delta. It's basically the z coordinate. This thing is the same as the z coordinate of the naked charge, plus J times the radius, the interaction radius, charge radius, cross section, whatever you want to call it, times the sine of the of delta. And of course, you will say, well, where is this part going? The cosine and the sine of the azimuthal angle. Well, it's in J. Is this a satisfactory wave function? Maybe it is, maybe it does. What means satisfactory? It means, can we use it in, like say you have a number of electrons and protons coming in, and there's some kind of huge collision, and we end up with a number of different final products, electrons, protons, going in entirely different directions with different kinetic energies. And there may be more electrons or positrons than protons, and whatever. You have one equilibrium situation being composed of many particles interacting, and in these high energy collisions, and resulting in a number of stable particles on the other side. And these stable particles are always going to be electron positrons, or a mix of their antimatter counterparts. But you end up with this formula basically, and probably you can't use it in a scattering matrix approach. And the other thing is, and that's more worrying, is that if you sort of interpret modern mainstream quantum theory as a theory of probabilities, where reluctantly mainstream quantum physicists will admit there has to be some kind of physical process behind, and these probabilities must be rooted in surface areas as compared to the larger area in which the particle which we study is to be situated in a crystal lattice, or an atom, or in a molecule. They're gonna say like, well, we take the square of the absolute value of this wave function for a proton, and we end up with 16 times the Compton radius of the proton. I'm not too worried about it. I'm going to my last slide now. I think you need to distinguish the concept of an effective versus a theoretical radius. I did that, and that's something I'm gonna pull up. In the context of to explain the anomaly in the magnetic moment of an electron, I said like, we need to distinguish indeed an effective radius and the theoretical radius of the orbit of the theta Boögen charge, and distinction needs to be made on the basis of the fact that infinitesimally small objects don't exist. You cannot load any property on them. So if you want to load charge onto a Titelbewegung charge as a property, then you also need to say it has some physical dimension. And this is the strange thing I put in this lecture here, where I mean, it's a series of lectures where I jokingly rewrote Feynman's lectures on quantum behavior, is that when you have the theoretical radius, but you do think about a charge that has a certain size, then in the orbit, as you see here, most of the charge will actually just a little bit more than half of the charge will be outside of that theoretical radius. And this is the funny thing, and I'm still sort of coming to terms with it, is that the effective radius of the motion of the Titelbewegung charge inside of an electron is actually larger than the theoretical radius. And that's a very funny thing, and philosophically I can't really explain it. I just know that it gives like the right calculations, I would say, to explain the anomaly in the magnetic moment of an electron. But here we are talking about what we have is a theoretical radius. When we put it into sort of a standard modern quantum mechanical interpretation in terms of well, this is an amplitude, and we're going to take the square of its absolute value, and then we have probability. We get these rather outrageous 16 factor. I don't mind about factor 2 or factor 4. 16 is a bit much. So that's where we're obliged to also consider that, when you calculate in all these experiments, which I mean, hat off for what people do. But they derive some kind of, we need to admit that, some kind of theoretical radius. And an effective radius is something else. I said, because the delta phi plane, the angle of, the plane that is formed by the polar and azimuthal angle spins around, the effective radius of this oscillation should also be smaller than what you would think based on its two-dimensional radius. Now, the thing is then, what factor should be used to relate this theoretical radius to an effective radius? What kind of model can we use? Well, there's sinusoids involved, sinusoidal functions. You're always going to have a 1 over square 2 factor that you must apply. I.e., if you're an engineer, look at it. A root means square of, a current or some other value that oscillates sinusoidally. The effective current or whatever is going to be 1 over the square root of 2 of the peak current. Or there is another argument which I found equally important or even more is, and I want to show that too. Yeah, here. Well, here is sort of really on the structure of electrons, protons, and atoms. I really want you to read that paper. But the basis of it is a paper where I derive the proton radius. So you have the pre-Radix experiment, experimentally measured, and so my model theoretically is the one that I have. Yeah, correctly. Because I first distributed this 4 factor over wrongly over. I actually modified Einstein's energy mass equivalence relationship at first. But the thing is sort of, the magnetic moments in condata, I realized that there was like a square root factor. And the square root factor, I need to prove that, but I think, when you have a magnetic moment that is generated by a ring current, or you put a ring current into some kind of a steady or changing magnetic field, it's gonna precess, and the precession of the ring current, sort of the axis of the ring current, or the axis of the magnetic moment, is gonna orbit around itself in a way that also respects the Planck-Einstein relationship. It's gonna incorporate. It's gonna have a certain amount of Planck's unit of action, and the amount that I posit, because we have boson formula, whatever, 1.5. I think the number that you have is going to be 1. This is the formula. It's sort of well, here I phrase it in terms of angular momentum. The angular momentum, that as you measure it in the z direction of the actual vector of the angular momentum, or the magnetic moment, is going to be n times h, as opposed to the total angular momentum, which is going to be h times this factor. I can't go back into the math. I think it's lecture 35 or 36 of volume 2. But for me, the question is then, of course, what is this n factor? Is it 1.5? Is it 1? Is it 2? For me, it's 1. Planck's quantum of action comes in full units, not in half units. And the illusion I would think that it comes in half units is just because, when you discuss elementary particles, we know half of the energy is going to be in the electromagnetic field that keeps the naked charge going, spinning around, and the other half is going to be in the kinetic energy of the naked charge. And that's sort of where this 1/2 factor, which puzzles so many, in Schrödinger's equation, in whatever, is it's kind of arbitrary. Matter particles are it's going to be sacrilegious to say, but they're spin-1 particles, and we can talk about geometric and magnetic factors. But in any case, the point I want to make is that you're gonna get this factor for the ratio between the angular momentum and the magnetic moment, as measured in the z direction, and the real magnetic moment, when you do not consider that it's precessing. So when we apply both these ideas to the idea of proton radius, we get an effective radius that is 2 times this sinusoidal factor, I would say, and then the precession idea. So it's going to be 1/2 times this theoretical radius, which gives us still 2 times h bar times c divided by the energy of the proton. You will say, well, it's still a factor 2 you need to get rid of. I'm going to be honest, my first publication, my manuscript got refused because Hestenes, who tried to revive the Titterberg interpretation, he still sticks with it. We had this discussion. He says still that the radius of an electron is 2 times the quantum radius, which, going back to this thing here, it's sort of like, yeah, you have a radius, theoretical radius, a quantum radius, and I can readily imagine that you would, in your model, arrive at a interaction radius, or whatever you want to call it, a charge radius, or whatever, that is 2 times that ring current radius, because it's not so neat. Compton scattering, I said these are theoretical constructs, and the magnetic field very near but outside of the ring current will still be very strong, and so you can have scattering of a photon just outside, and if then it's just 2 times that radius, or about 1.7, the radius, these things are going to be there. We are talking about, and now I'm going to talk as an IT project manager about, logic that is clear and acceptable to all, but it's still kind of a fuzzy logic. So when we then calculate, the square of the absolute value, which we use in, mainstream interpretation of quantum mechanics, and that's to derive probabilities from some kind of wave function, we're still going to have, 4 times a 4 times the squared Compton radius of a proton, but that's kind of acceptable if you look at, Kodata values. For like charge radii cross section, you're going to have something like 8 times 3 p r squared. 8 times, so that's almost, but not quite. 9 divided by 3, that's something close to 3, but not quite 3. Or a 4, 8 divided by 2 is 4, of course. The main thing I want to note here, and that's something you should know, and I really encourage you to sort of develop your own theory or realistic interpretation of what quantum mechanics is about, is Feynman. I really hesitated because, the Guardian, appointed by MIT for Feynman's lectures, took a video of line, pestered me on my readingfeynman.org site, and he got right. But I just gonna quote him. One of the very early introductory lectures to his third volume of lectures on physics, which is on quantum mechanics, is he talks about the size of an atom and gives a very intuitive model of the Bohr radius, but he still says, and that's something I really remember, and he says, this model that he offers is just a kind of dimensional analysis, and we need not trust our answer to within factors like 2 or pi, etc. Especially, and this is something new, which I did not mention in previous video lectures, we do not even have defined a very precise, I didn't write it out, a very precise definition of what A is, of what is radius. Is it a radius, a charge radius, or a cross-section radius, or an RMS thing of, what is it? And that's what I'm saying here. The Compton radius, an RMS charge radius, scattering cross-section, these are all very precisely defined scientific concepts. And I'm not sure that I respected these very precisely defined concepts for what a radius or the size of a particle actually is in all the models and all the stuff I wrote. So I'm not worried. I think I'm on the right track, and I really encourage you to challenge what I talk about, and yeah, do that. My next, so this is the second in sort of a very new series of a new playlist I want to develop. Next time, I'm really going to be talking about the structure of atoms and molecules and energy states and the mechanics, I would say, of modern quantum theory. I think quantum theory has its advantages. Modern quantum theory, in terms of, it's pretty much a huge step forward from the primitive probability theories that Einstein himself pushed when, explaining the Brownian motion. Um, for which he in the end got a Nobel Prize rather than his special relativity theory. Um, so it's very interesting, and I'm going to be talking about that in my next video. I apologize for this very confused talk, and but at the same time, it's I said, for me the purpose really is now to have fun, which with the work I did, which was hard, and now things are a bit downhill, and I just need to, promote what I wrote about, and secondly, really move to the next stage, and that's sort of to explain real life phenomena like this Rayleigh scattering. Everybody knows the formula, but what's the final explanation for that? Why is the sky blue? I thank you very much, and I talked for almost an hour. That seems to be my standard, and I wish you a very nice evening from Brussels.